Dear participants, due to network issue, our resource persons left from this session. We thank for the, for his wonderful opportunity to share with us his research knowledge. Uh, Anyone wants to his number is available in the chat box. Please take it and discuss about his research items.
Hello, sir.
Sir, Ramkar sir, please welcome.
Yes, sir.
Yes,
Thank
please.
you, sir. Shall I start the session, sir?
Sir, just a minute, sir. I'll give the case. Yes, sir, please welcome. Here, Dr. K. Ramkumar, Professor in Mechanical Engineering from Dhanlakshmi Srinivasan University, Chapalli, Tamil Nadu, is here with us. He has obtained his doctoral degree from Anna University, Chennai, in the area of titanium-based advancements of medical imbalance and devices. He has published many research articles, patent relevant his research area. Now I invite Dr. K. Ramkumar sir for the session without time delay. Sir, the forum is yours, please.
Sir, can you hear me?
Yes, sir.
Okay, sir.
Audible,
Thank you,
sir.
sir. Thanks for your introduction. First
Thank
of
you.
all, I would like to thank Dr. Manivel, sir, and Mr. Prakash for giving me this opportunity. And thank your institution and my institution for giving me this opportunity. Shall I share my PPT, sir?
Yes, sir.
Can you see the slide, sir?
Yes, sir. Is
Okay,
it
sir.
okay?
Okay, sir. Thank you, sir. Uh, The topic given to me is advancement in titanium-based solution for medical implants and devices. Myself, Dr. Ramkumar from Dhanlakshmi Srinivasan University. The overview of this presentation is first I will start with the human implants. After that, materials used and why titanium is preferred. After that, various implants of titanium used. After that, what is meant by titanium? What are its mechanical and chemical performance of titanium. After that, surface modification for enhanced biocompatibility, wear resistance, and corrosion resistance. After that, how titanium is prepared for implants. And the final one is conclusion. So, first of all, we will discuss about human implants. Actually, human implants is nothing but it is a medical device or a tissue that placed inside or on the body. Okay, implants can replace the missing parts, or it can support the structures. For an example, it can support the bones or any parts of the body. The various types of implants are first it will start with the prosthetics. Okay, the in prosthetic it replace the missing body parts. For an example, it can replace the artificial limbs or prosthetic eyes and ears, like that we can implant. The next one is body function monitoring. The main purpose is to monitor the functions of the heart rate, glucose levels, or other physiological parameters. For an example, the glucose sensors or wearable health monitors like watches they'll be using. After that, pacemakers, these are used. The next one is about organ and tissue support. Uh, this in this implants, it helps in function of organs and tissues. For an example, artificial heart valves or joint replacements. The next one is about brain implants. And brain implants, it helps in to communicate with the brain and the action or about the neurological conditions. The examples are the cochlear implants. Uh, if there is any hearing aid problems, they will be using cochlear aids. The next one is about dermal implants and the subdermal implants. These are placed in the skin for medication delivery systems. The last one is about dental implants. It is used for replacing the uh, uh, teeth or for tooth roots. Here the titanium screws will be used to support the artificial teeth. The next one is about implant materials. Human body must meet the following essential requirements. Uh, First one, let us see with this diagram. It is about compatibility. In compatibility, the tissue reactions, the implant which you are placing inside the body, it should react with the tissues. In that way, the material should be made. The next one, change in properties. The material should change with respect to mechanical, physical, and chemical. The next one is about degradation. Uh, it should not affect the. It should not be harmful to the systems. And the next one is about the mechanical properties. In mechanical properties, first one is about plasticity. The material which we are using should be uh, easily shaped to the required. So, suppose for example, uh, we are using any knee bone, means it should be easily shaped for that shape. The next one is about yield stress. Yield stress is nothing but the minimum stress required. The material which we are forming, it should be formed with a minimum force. The next one is about ductility. Ductility, it's about it should be ready to uh, deform without breaking. The next one is about toughness. The toughness is nothing but it should be strong enough and it should not be broken easily. The material which we are making, it should be strong enough. The next one is about time dependent. In time dependent, it should in a frequency of time it should integrate with the bone and it should not produce any infection to the bones. The next one is about deformation. It should not deform with respect to the external forces. And the next one is about it should have a it should be creep. The creep resistance means it should withstand deformation over time. The next one is about ultimate strength. It should ultimate strength means should withstand more strength. The next one is about fatigue strength. So fatigue strength is nothing but it should not uh, break even more. Even repeated loads are given. The last one is about hardness. It should be hard enough, and the next one that hard enough means it should not be. It should resist the scratches and indentation. That is the hardness requirements. After that, wear resistance. Uh, it should not wear due to the friction. Okay, so these are the mechanical properties which should be the material which we are using should have. The next one is about how it is manufactured. It is either it can be fabricated or using synthesis method it can be made. Synthesis means respect to nano level it will be made. Next one is the consistency of the requirements. After that, the quality of the raw material should be good. Uh, After that, it should be the capability of material to get safe and efficient sterilization. And the last one is about cost of the product. So these are the requirements which the materials which you are using for implant should meet. On the side also we can see the four main properties. In these properties, these are the four main properties. First one, mechanical properties. It should high strength and hardness. The next one, biocompatibility. It should not be toxic and allergic to the human body. It should not release any metal ions. Suppose if it is releasing any metal ions, means it will make severe harmful effects. After that, we have to again remove the implant and we have to do the surgery again. Uh, the last one is about osseous integration. The osseous integration it should be suitable to the adjacent bones. So, what are all the different reasons for undergoing revision surgery? So, as I said before, these are the requirements which should be met for implantation. If suppose these are not met, what are the what will happen and what are the different reasons for undergoing revision surgery. The first one is about infection. So the infection is nothing but due to the bacterial contamination. After surgery, there means some, if suppose the infection is happening, means again we have to remove the bone or whatever may be the part which you are implanting. After that, loosening. Over time, if it will loosen, suppose if we are giving more stress, if you are giving more stress to the implant, means then it will the implant will get loosened. The next one is about bone resorption. Bone resorption is nothing but the density of the bone will get reduced. The subsequent density, suppose if the implant is connected to another bone, means that bone, if it is not properly, the modulus of both the material is not meeting properly, means then the density of the adjacent bone will get reduced. After that, allergic reaction. In the allergic reactions means suppose if it is releasing some metal ions, means then it will cause pain, swelling and skin rashes. These are the allergic reactions. uh, After the next one is about synovitis. So this is inflammation happen when wear particles, when a wear is taking place in the implant. The next one is about the implant uh, fracture. Suppose if we are giving more strain to the implant, means then it will get fracture. And the next one is about systematic complications. Suppose if, as it said before, if it is releasing any tear or if it is releasing any metal ions, means then it will affect. It may affect the heart or neurological changes or thyroid complications may occur. The next one is about soft tissue complication. The tissue which is connected with the implant may get tear due to when it is more harder. Next one is about dislocation. In dislocation, if it is not aligned properly, means then the dislocation may happen. Uh, After that, mismatch in Young's modulus of elasticity. In modulus of elasticity, as I said before, if the elasticity of material under the bone is not meeting properly, means then we have to again remove the material. The last one is about wear and corrosion. So wear will have a due to friction. So uh, so what are the materials used in implants? So here we will see what are the materials utilized in orthopedic applications. Majorly, there are four categories. The first one is about metals. The next one is about polymers. After that, ceramics and natural materials. So metals, in metals, the titanium, stainless steel, cobalt, chromium alloys, and tantalum. These and all comes under metals. So these are used in implants when there is high mechanical stress, uh, like joint replacement, bone plates, screws, rods are needed. So there metals are used. The metals can withstand more loads, as titanium is excellent biocompatibility and resistance to corrosion. The next one is about polymers. In polymers, Polyethylene, for an example, it is used. Polymers are maximum used in the joint replacements. For example, for bone cement, for implants, they will be using it. The next one is about ceramics. In ceramics, zirconia is one of the ceramics which is used in dental implants. We can see the zirconia. The next one is about natural materials. In natural materials, the materials like collagen, hydroxyapatite, these materials are used as natural materials. So these natural materials are used in bone crafting or scaffolds. And if there is any osseointegration is needed, means they will use natural materials. Osseointegration is nothing but it helps in bonding the implant material with the adjacent bones. So under metals, what are the types of metals which we are used? So metals have been extensively used in orthopedics. The first one is about stainless steel. Stainless steel is a durable, ductile, and corrosion-resistant metals. It is used as a plates, screws, and hip nails. Maximum low carbon steel, that is 316L materials is maximum used. The next one is about titanium. In the titanium, it is a lightweight, durable, and corrosion resistance. It is often used in dental, knee, and hip replacements. Uh, the next one is cobalt-based alloys. It is a non-magnetic heat resistance and corrosion resistant metals. It is used for joint replacements, hence it is having a good load bearing capacity. And next, gold, zirconia, and porcelain. These three materials are maximum they will be using in dental applications. The gold, it is a biocompatible material that long lasting and durable. But gold give a distinct appearance when we are using it in dental. The zirconia is strong and it's hypoallergenic ceramic. Some peoples will be allergic to the metals, so they will go to zirconia or porcelain. Porcelain is used for crowns. Titanium will be used as a root, and porcelain materials will be used as a crown. So these are the various parts of the body where the metal implants take place. First one is about cranial implant. In cranial implants, we can see titanium and titanium 6, aluminum 4, vanadium. It is used in cranial implant. Then stainless steels. After then, coronary artery stent. For heart, we are using a cobalt chromium alloys and nitinol. Nitinol, nitinol is about nickel and titanium alloy. The next one is stainless steel. After that, for joint replacement, we are using cobalt chromium alloys and titanium and stainless steels. The next one is about a bone fracture implant. And bone fracture implant, cobalt chromium alloys, titanium, and stainless steel is used. After that, a dental implant. Uh, in dental implant also, cobalt chromium alloys, titanium, they are using. The next one is about bones scaffold. Bone scaffold is nothing but when there is any problem in any tissues, like there are suppose if any bone is degraded due to any disease or bone disease, there they will use these kind of materials. Then also integrated implant. So here they are using titanium and stainless steel. So here you can see how a material how our immune system react with the biomaterials when a new foreign object enter into the body. So first, in here you can see in certain seconds, the water molecules get absorbed with the bio material. After that, it will absorb the proteins. Uh, After that, the immune system starts, for an example, the macrophage and neutrophils will start the immune system. That is, it release some enzymes and it will fight with the biomaterials as some foreign materials has entered. So after that, here you can see it will finally it will create a fibroblast like materials. it will close the total material, and it won't react with the internal body. So our immune systems will make these kind of reactions. So we have to create a biomaterials, so that we can trick the immune system, and we can make the biomaterial to react with the internal body. For this, I would like to show a video. Second.
Insulin pumps improve the lives of many of 415 million people with diabetes around the world by monitoring blood sugar, delivering insulin, and preventing the need for constant finger pricking and blood testing.
So, once again. So here you can see once again. In earlier days, they used insulin, using the pumps to monitor the blood sugar. Here you can see the delivering the insulin in using the pump and needle. The small machine is used. How much insulin to deliver through the needle? Okay, so during some in certain days we have to move the needle inside the body. This is because of the immune system. There are various parts. So these are the immune systems. So here you can see the macrophages and neutrophils. So these will try to destroy the external objects. So suppose a needle is injected inside our body, means it will think it is a virus or a bacteria. In the same way, it will think. So the antibodies will stick over the body, and it will give signal to the other immune cells. So all the white blood cells or immune cells, like the macrophage and neutrophils, they will start releasing the enzymes and to degrade the materials. Here you can see. If it is not possible, means everything will join together. It will form as a giant cells. And at the same time, the fibroblast, it is also fight against the foreign body. So it will try to stop the work. So here you can see it is completely close to the needle inside the body. So in this way, our immune system will make the implant not to work properly. So for an example, they are saying pacemaker. If the pacemaker is giving any signal, means this immune system will stop even the pacemaker not working. So the researchers are working, many works are made to trick the immune system. So I just want to make this slide clear, so I am sure that video. So we have to resolve these kind of problems. If you are not resolving these kind of problems, then the inflammation will take place, and as shown in the video, it will create a fibroblast, so that it will make the material not to react with the adjacent bones. So depending on the biomaterial's nature, the body's response might resolve. The main thing is both surface chemical composition and the topography plays significant roles in the implants. That is the type of what type of interactions it is making, and biochemical absorption. For an example, formation of calcium phosphate layers and the interaction with the macrophages and the bone marrow cells. So this if it is not, if the implant is not create material is not created properly, then it will, the implant will get failure. So why the titanium alloy is preferred as from the topic? Titanium alloy is preferred because it has good biocompatibility. It is not harmful to the body, and it is well tolerated to human tissues. And the next one is about corrosion resistance, especially in moist and salty environments of the body. It won't corrode, and it has it can withstand stress and pressure without being excessively heavy. The titanium, when compared to other materials, it will be half the weight of the other materials, but it can withstand more stress and pressure. And the next one is osteointegration. It can easily bond with the other bone tissues, and it is not toxic to the it is not toxic to the internal body organs, and it has a low risk of due to its compatibility with the human tissues. The rejection is very less. So, as I said before, the main advantages are it has inertness, strength to weight ratio, and flexibility in mirroring bone and the protein absorption. So these are the advantages when compared to other stainless steel or chromium cobalt alloys. So the uh, mostly the titanium alloys are like commercially pure titanium or titanium 6 aluminum 4 vanadium are used in clinics. Uh, However, the titanium alloy has a higher Young's modulus when compared to the uh, human bone, which may induce a stress shielding effect. So this stress shielding induces bone resorption. Bone resorption is nothing but the density of the bone will get reduced. Uh, so this is reduced by incorporating vanadium and sorry in additional this titanium 6 aluminum which it is also toxic and it cannot be used for long term use, which can give diseases like Alzheimer's disease or peripheral neuropathy disease. So here you can see the image where the stress shielding effect. Stress shielding is nothing but here you can see the left side. The stress is applied from the top and it is evenly distributed to the bottom bone. However, here the stress is not evenly distributed, so the lower bone will have reabsorption. That is, the density of the bone will get reduced. So that is the problem of stress uh, shielding effect. So to reduce the toxic elements, they are incorporating tantalum, niobium, and zirconium. The two main things we have to improve the biocompatibility of titanium and its alloys. First, we have to reduce the toxic elements. After that, we have to improve the surface modification for improving the osseointegration and antibacterial properties. Because if you are improving the osseointegration properties, means the implant will easily bond with the adjacent bones, and by reducing the antibacterial properties, we can reduce the infection. Uh, which will create an inflammation. After that, it will create a pain and swelling in the particular area. After that, now we are going to see some common applications of titanium alloys in medical implants. The first one, it is used in orthopedic implants. The titanium alloys in orthopedic implants, it is used for hip and knee replacements, especially when the load-bearing implants, since it is having high strength and more resistance to corrosion. The next one is about dental implants. In dental implants, it is a better choice. So it is replaced for missing teeth, and it provides a strong foundation. After that, it is used for bone plates and screws in. Suppose if there is any surgical repairs in fractured bones or joints, here the titanium is used. After that, spinal fusion devices. If there is any spinal disorders, there the cages, rods, screws. Here the titanium is used. After that, heart valves and pacemakers. Here also in cardiovascular implants, this titanium is used to keep the. It is used as a casing to keep the devices inside this casing. The casing will be made of titanium. After that, craniofacial. Suppose if any facial bones are get fractured, so here also they are using titanium. The next one is cochlear implants. Suppose if a people is having any hearing loss, means here the titanium is used. Here also the device is placed inside the titanium casings. So first, here we can see uh, orthopedic implants. So suppose if there is any accident, if there is any injuries, means here the titanium is maximum used. Suppose if any external treatment is not sufficient to recover, since titanium is having a higher strength to weight ratio, and it is having a higher compatibility and corrosion resistance. So it is mainly used in hip replacements. After that, knee replacements, shoulder replacements. After that, it is used in fracture fixations like titanium plates, screws, rods are used for this. And there are also some challenges like a bacterial infection, metal overload. As I said before, if the material should be made with proper X modulus. The next one about inadequate stiffness matching. Suppose the titanium which we are using is more stronger or having more weight than the adjacent board, means this will make unnecessary pain swelling inside the, and it will finally create an implant failure. So the next one is titanium used in dental plants. Here you can see the dental where the titanium is used. Here it is used serving as a foundation material which the implant root is craft. So the screw-like post we can see at the bottom. Here it is inserted inside the jawbone. Since it is having good osseointegration, it creates a strong and stable bond, and it acts as a natural tooth-root relationship will get created. So it provides a better support to the upper dental crown. It helps in withstanding a better load. For suppose we are chewing and biting, means here it can withstand better load. Uh, Here in dental, the biocompatibility, it is not harmful to, or it is not toxic, uh, and it has a good stability and longevity in the implant. So here this minimize the inflammatory reaction, since it is compactable and it is not harmful. So it minimize the inflammatory reaction, and the healing process will take place in a better way. The next one is about strength and durability. So mainly strength and durability is the fundamental things need in an implant. So, it won't corrode easily, so it can uh, it has a more success rate, and it will create a better satisfaction for the patients. So with respect to versatility, the titanium materials in a dental, we can make the shape of with any shape or any sizes which is required for the implant. And moreover, it's compatibility with the various implantation techniques. Suppose traditional implants or immediate implants. Here uh, it underscores better adaptability. Sometimes, as I said before, titanium may be allergic to some peoples, so we have to make a better test before implanting. And with respect to aesthetic limitation, suppose if the gums are very thin, means the titanium can be seen when they are having a high smile line. That is, the metallic base of the implant will be more apparent when smiling. The next one is about skull implants. In skull implants, it is used for to reconstruct the skull and treat cranial defects. Uh, Here also, it is having good biocompatibility and strength, and it is lightweight. So here you can see the titanium plates. It is used for calvarial fixation and reconstruction. In the top image, you can see the calvarial fixation. Suppose if there is the skull is not properly closed, means they will use the titanium plates for these purposes. After that, the titanium mesh will be used. Here you can see the titanium mesh. If suppose if there is any the skull is broken, means they will use this kind of titanium mesh to restore the skull defects. uh, this can be easily 3D printed, and also some incremental forming process also they are nowadays they are using this uh, we are making this kind of a skull. Next one, titanium in spinal fusion devices. The titanium is used in spinal fusion devices such as rods, cages, and screws to provide stability and promote bone growth. Uh, Suppose if there is any bone disease and the spinal, if they want to remove the spinal, means there they will be using this titanium mesh cages. Here at the bottom, you can see they are using a mesh like titanium in the place of removed spinal area. After that, the titanium rods are used to improve the stability of the fusion. Here you can, the top you can see the titanium rods are used to improve the stability. After that, the screws also used in this spinal fusion device. So the cost is more. These are the challenges. The rest of the things we have seen already. The biocompatibility, and it is easily 3D printed. So titanium in hot walls and pacemakers. So titanium, since it is strong and resistant to corrosion, it is used in hot walls and pacemakers. Titanium is blood compatibility and resistance to degradation. The next one is about endothelization. In endothelization, you can see the slide. You can see first the biomaterial will be texture, surface texture. After that, the chemical modification will takes place. When the biomaterial is uh, modified, after that it should the biological modification should takes place, so that it will reduce the risk of embolism. The embolism means risk of having blood clot in the walls. So this should be reduced. And the next one is about pacemakers. So pacemakers is a, since it is a corrosion resistance, it is used in the internal components because it works in better in the moisture area. The other things are artificial hearts they are using. They are using a circulatory assist device here. The left diagram you can see. It is helping. Suppose if there is any diseased aortic valve means it helps in regulating the blood flow, and also they are using stents. Suppose if there is any block in the blood valves means they are using uh, stents to remove and enlarge the blood valves. The next area where the titanium is used is craniofacial plates. Here, the titanium is used to reconstruct the face or skull, and it is used for fixing the bone plaques. The various uses are the bone plaques after craniotomy, and in the previous slide we have seen in the skull, if there is any problem means they will be using this titanium. After that, they can reposition, used for reposition, stabilize the jaw. Uh, it is also used for fracture fixation. Suppose if there is any person meet with any accident, if there is any fracture in the facial bone means the titanium is used to fix this facial bones. After that, if there is any, if you want to improve the jaw alignment means there also they are using the titanium. After that, for repositioning the jaw structures, there also they are using this titanium. And as I said before, if there is any joint fracture or dislocations also they are using. If you want to improve the facial aesthetics means there also titanium plates are used. The titanium is has better biocompatibility. It provides more rigid fixation than suture. Suture is nothing but putting stitches. Uh, Instead of that, we can use titanium plates, and we can use the screws to fix the uh, bones or jaws. The next one is about cochlear implant. So the titanium is used to implant housing and screws. Here you can see the implant is made. The microphones will be, you might have seen in some people, they will be having these microphones. Here the cochlear implant, it will be attached with the skull. So it should be biocompatible. It should have good strength. It should be stable. It should not react with any magnetic fields. So these are the things which you need when you are going for the cochlear implant. So here the housings and the screws which are used to make the device are made up of titanium. So there's just how we are the previous things we have seen where the titaniums are used. Where are the areas where the titaniums used? It's just a introduction about titanium. Since I didn't give any introduction about titaniums, it is a most abundant material, fourth most abundant material in the air, apart from aluminum and magnesium. So it is half the weight of, for an example, steel, but it can withstand the same stress or pressure. So it can be modified. Its properties can be modified when various alloying elements are added. So it has the following properties, like it has a good strength, it is light in weight, it has high corrosion resistance. It has good aesthetic. It is no need for maintenance. It is less expandable. Suppose if there is a any thermal expansion means it less expandable. It is friendly to humans, and it won't the oxide layer photocatalysis. It is the oxide layer on the surface is strictly controlled. It is flexible, and the final thing is it won't give a perception to of coldness. This is the main thing because when we are implanting this, metal inside our body, it should not give coldness to the human body. This will make uncomfortness. So the various classification, as you all know, this classification depends upon the composition and the phase structure which they exhibit. This composition phase structure will determines its mechanical properties and the applications. So the broad categories are alpha, beta, and alpha plus beta alloys. So in alpha alloys, the titanium is a major one. After that, it has small amounts of aluminum. The properties are it has good weldability, formability. It has lower strength than beta alloys, but excellent creep resistance and corrosion resistance. It has a lower density and good fatigue strength. It is uh, it has more applications in aerospace and medical industries. For an example, they are given as dental plants, aerospace and all. Nowadays the turbines and all they are using titaniums. And the next one is beta titanium alloys. Uh, in beta titanium alloys, it is primarily composed of body-centered cubic crystals. Uh, Here, the elements such as vanadium, molybdenum, and niobium and chromium are also available in these materials. Its properties are it has a higher strength and better formability. It has a greater resistance to uh, fatigue. That is, it is having better capacity for load bearing applications. Since this beta type titanium alloys are maximum, they will use in orthopedics. Uh, the main uses of this also, it is used in aerospace, automotive, and medical implants. So these are the examples of beta titanium alloys. The next one is alpha beta titanium alloys. So it has both the properties of both the alpha and the beta phases. It has a good strength, ductility, and hardness. Here the composition of elements like aluminum, vanadium, molybdenum, and niobium are also available. So here also it has good strength and ductility and corrosion resistance. So uh, can be heat treated to achieve a wide range of mechanical properties. This kind of materials is also used in aerospace, medical implants, and automotive industries, like hip and knee replacements. This kind of titanium alloys are used. In the examples, you can see titanium 6 aluminum, 4 vanadium, Ti6Al, 4B. This is maximum used in aerospace and medical applications. And the next one is Ti6Al, 7Nb. Uh, Here it is used for medical implants, since it is having a better biocompatibility. As I seen before in the previous slides, we can see niobium helps to improve the better biocompatibility of the material. The next one is about commercially pure titanium alloys are also available. It has um, minimum of other elements, maximum it consists of oxygen. So it has a better corrosion resistance. This is also used in medical and industrial applications. This is also it has a better strength. So it is also used in dental implants and surgical instruments and some non-load bearing orthopedic applications. The last one is about near alpha titanium alloys. It has a small amount of beta phase. So this alloy has properties of excellent creep resistance, good weldability, and moderate strength. Uh, it is suitable for high temperature applications. It is used in aerospace and industry applications. The final one is about shape memory alloys. The titanium, uh, the shape memory alloys plays a significant roles. That is it is as you all know, shape memory alloy is nothing but it has the ability to remember the original shape after undergoing deformation. When the external force is removed, it can regain its original shape. That is a shape memory alloys. So the common types of shape memory alloys which are available is titanium nickel, titanium niobium, and titanium tantalum. These are the common shape memory alloys available. So the main key features are it has a better shape memory effect. It has super elasticity, and the next one is it has a better biocompatibility. After that, it has a better corrosion resistance. So these are the key features of the shape memory alloys. So these shape memory alloys are mainly used in bone implants, tissue engineering stunts, joint replacements, or other orthopedic applications. So here we have seen the advantages of titanium when it is used in shape memory alloys. I when we are using shape memory alloys, less invasive surgeries uh, can be made. For an example, we cannot, no need for to make a uh, maximum cut in the body. A lesser cut we can make in the body, and we can make the surgeries. And it has super elasticity properties, so it has a reduced risk of implant failure. And the next one, it has a biocompatibility and long-term use. The last one, it is effective for complex anatomy structures. So this is one of the example where the shape memory alloys are used. Here you can see the nitinol, that is titanium nickel. When the stent is inserted into the blood valves, here you can see the artery, the balloon catheter, and a closed uh, titanium nickel stent. And here you can see the plaque formation in the uh, blood valve. So this stent is inserted into the blood valves, and this balloon catheter, when a balloon catheter expands, this titanium nickel stent will also expand. After that, the balloon is retracted, and it is extracted from that particular place. The stent will kept on that place. So here in the last one, last image 3, you can see the stent is placed. So it will elongate that plaque formation, or it will remove the plaque formation. So like this, the shape memory alloys will work. The final one is the summary of the titanium alloy, which we have seen in the before slides. So we have seen alpha, beta, commercially pure, and near alpha. First one is alpha. It has a higher corrosion resistance, good fatigue strength, formable, and it is used in aerospace, medical implants, and dental. The next one is about beta. The beta has a high strength, excellent fatigue resistance at elevated temperatures. It has common uses in aerospace, automotive, and load-bearing implants. The next one is alpha plus beta. It has balanced strength, ductility, corrosion resistance. It is also used in aerospace, orthopedic implants, joint implants. The next one is about commercially pure titanium. It has high biocompatibility, excellent corrosion resistance. It is also used in dental implants, surgical instruments. Next, the last one is near alpha. It has alpha plus small beta. It excellent creep resistance, good strength at high temperature. It is used in aerospace, industrial components. So these are the areas where the titanium alloys are. What are the titanium alloys used in various areas? In the previous, slide image like this, we have seen various metals which are used in the human body. This image shows various titanium materials which is used in the various parts of the human body. Here we can see the dental base and all. They are using titanium 6 aluminum 7 niobium. The next one is about the elbow joint, what kind of composition materials they are using. The next one is about hip joint. After that, the dental implant, and the shoulder joint, spinal spacer, the knee joint. So the various kinds of materials which is preferred for a particular area for their better working. So in order to make the titanium work better, we have to incorporate some alloys in the materials uh, to improve its mechanical and chemical performance during the implants. The various processes are there, for example, solid solution strengthening, precipitation, grain refinement, or work hardening. So this help to balance the uh, strength and things, elastic modulus, to improve the implant efficiency. First, with respect to strength and ductility, elastic modulus, here we can the strength and ductility are the main important factors needed for a material. Uh, for example, if you are incorporating vanadium, aluminum metals can help in transition between phases from alpha to alpha plus beta. Therefore, it can improve the strength of the alloy. Uh, you should not also improve. You should not also make the concentration of beta stabilizers more, so it will lower the alloy's resistance. The alloy's resistance is increased means it will reduce the biocompatibility. It won't make a proper bond with the adjacent bonds. So that should also be taken care. So the beta alloys helps in a favorable elastic model compared to the modulus of the uh, human bone. Uh, so the next one is about wear resistance. So wear resistance, the material loss due to the mechanical actions like sliding and rolling. When the friction takes place between the materials and the bones, here the material loss will takes place. So this wear will lead to device failure, and it may release some particles which will affect the it will create harmful reactions inside the body. The main two wear uh, which will take place is abrasive and adhesive. So uh, the in our human body, the main wear which will take place is adhesive wear. Uh, in the titanium alloys primarily experience wear due to adhesive interactions or abrasive actions or tribochemical reactions leading to oxide layer formation and fatigue induced micro cracking. So these things you should be controlled by uh, optimizing the surface oxide properties using some chemical modification and using nano-grained materials. The next one is about fatigue resistance. So fatigue resistance is nothing but uh, when uh, frequent load or number of continuous load. If you are suppose we are star walking, if you are walking on the stairs, and if you are giving too much loads to that particular implant means, then this fatigue will takes place. So here also the ultra fine grained structures helps in reducing this fatigue resistance. This is acquired by uh, cold rolling or short peening, which will introduce compressive residual stresses in the implant. The next one is about corrosion resistance. Since the material is in contact with the body fluids, uh, it may create a corrosion, uh, and like a
it may release some metal ions or whatever it may be, which will be harmful to the human bodies. So in the human body, the artificially implanted alloys or composites may undergo various chemical reactions uh, involving the oxidation of metallic components. So the various kind of corrosions like pitting, crevice, galvanic, intergranular, or corrosion fatigue or fretting corrosions, which will takes place. They can these materials can corrode when, for an example, if in a dental implantation and all, that titanium may get corroded when high fluoride solutions are used as in when the paste which we are using may contain high fluoride. So this will affect the titanium. So this corrosion can be reduced by addition of the alloying elements like niobium and tantalum to the titanium alloys. So it will this addition of niobium and tantalum will reduce the release of the metal ions. Uh, the corrosion behavior will so also influenced by its composition, microstructure, and grain size. So said in the previous, I said in the previous slide, the even distribution of the niobium and tantalum across the alloying phase will help to reduce the corrosion. So proper alloying elements should be chosen and optimized heat treatment should be made. The next one is about corrosion and fatigue. So both, suppose if both the corrosion and fatigue takes place, the material should resist. Here you can see the combined effects of cyclic loading and corrosive psychological environments can further accelerate material degradation, which will reduce the lifetime of the orthopedic implants. So here also the influence of alloy composition, surface condition, and microstructure acts a major role. Uh, for example, the corrosive fatigue behavior in titanium is significantly affected by their microstructure also. The laminar microstructure is sensitive to environmental condition, leading to notable increase in crack growth rates compared to the bimodal and millennial microstructures. So in the previous slides, we have seen how to improve the mechanical and mechanical and physical properties. For example, wear resistance, corrosion resistance of the material. Here, from the slides, we are about to see the how we can modify the surface to enhance its biocompatibility. So the titanium is alloys is extensively used in heart tissue replacements and cardiovascular applications. The titanium alloy exhibit bio-inert properties despite their outstanding biocompatibility. So, as a result, the fiber capsules do not form around the orthopedic implants, leading to mechanical osseointegration between titanium alloy implants and bones. Do not uh, make strong chemical bonding. So this should be reduced using a proper surface modification. Secondly, due to inadequate resistance to plastic shear work hardening properties and the poor addition of the surface oxide film, the subsurface of titanium alloys may remains vulnerable. So the bad titanium alloys cannot be effectively withstand the adhesive and the abrasive wear. So for these reasons, the surface modification should be take place. Uh, and also the third one is about uh, uh, the titanium alloys can naturally, even though it can naturally develop their own passive layer surface, which will have excellent corrosion. It may get peel or it will get dissolved. So these things should be stop because it will release harmful substance or the wear debris which is toxic, and it may cause inflammation, uh, and also it may lead to blood clotting within the body. So here you can see what are the benefits of surface modification. It will increase the better corrosion resistance, biocompatibility, targeted therapeutic delivery, better wear resistance, and better integration. Uh, Next one is about the bioceramic bioactive coatings. Suppose these bioactive coatings are given using a plasma spraying, electrochemical deposition, sputtering, dip coating, then ionic growth methods, sintering, and micro oxidation. These coatings includes the coatings which they are using is about hydroxyapatite, fluoroapatite, and the beta tricalcium phosphate. Like this, they will be using various coatings. Uh, Here I have taken hydroxyapatite. This hydroxyapatite it's extracted from the uh, uh, human tissues, which helps in creating a new tissue growth and prevents the metal ion. When we are giving this coating over the uh, titanium alloy, means the metal ion leakages is get controlled, and it helps in generating a new tissue growth. So hydroxyapatite is nothing but a primary component of human bone and teeth, which has a superior biocompatibility, promoting bone tissue growth on coated implants and reducing metal ion release. So this when this hydroxyapatite coat is given over the titanium, it helps to promote faster osteoid formation when compared to uncoated parts. Sometimes these coatings will have low bond strength and a high residual stress. Hence, they are also using intermediate layers like zirconium oxide and titanium oxide when they are using this hydroxyapatite coating. And as I said before, they are using beta tricalcium phosphate, and they are also using wollastonite and diopside. So they are also using in a surgical suture. They are using a bioactive bioglass nano powders, which will help to increase the biocompatibility. So surface treatments for titanium nickel alloys. This titanium nickel alloys is nothing but shape memory alloys, which we have seen in the before slides. So here also the releasing of nickel ions should be reduced. So the application of heat treatments leads to formation of titanium oxide layer on the titanium nickel surface, which optimal results observed out 450-degree reduce the release of nickel ion. The next one is about antibacterial properties. So the antibacterial properties should be improved in order to reduce the infection which will takes place in the implants. So here they are using a silver plasma emulsion to develop titanium oxide nanotubes containing silver particles on commercially pure titanium, which is suitable for the dental purposes. So the next one is about surface modification for improving wear resistance. Here you can see the mainly they are making uh, surface modification three ways. First one is about a physical surface modification. The second one is about chemical surface modification. The third one is about mechanical modification. Physical surface modification, they are making ion implantation, laser cladding, physical vapor deposition, and plasma spray coating. In the chemical surface modification, they are using chemical vapor deposition, electrochemical treatment. Mechanical modification, they are using polishing, grinding, and sandblasting process there. Here you can see the titanium nitrate and the diamond-like carbons are used in physical deposition. And the next one is about surface modification for improving the corrosion. Here the titanium alloys are widely used in orthopedic and dental implants. So here the corrosion resistance should be improved in a better way. So many techniques are used to improve the corrosion and resistance of the titanium material. For an example, here you can see the titanium grade. Here the various kind of reinforcement are used, which will create a certain composition. And here they are given a processing methods. And the key results are also given. The various processing methods which they are using is atmospheric plasma spray, selective laser melting, and selective laser melting. For example, they are using titanium 6, aluminum 7, and niobium. The reinforcement they are using is hydroxy uptake. Reinforcement is nothing but it enhances the strength of the material. So the various process maximum they are using is selective laser melting to improve the resistance of the material. So there are various methods are there to create the titanium composites. The first one is about titanium ceramic composites. So this titanium ceramic composites is is a promising material for orthopedic implants due to its strength and wear resistance and biocompatibility. So here in the titanium they are including a hydroxyapatite and a calcium phosphate and olastenite. So this helps in when this ceramic is coated over the titanium implant, it increases the strength and bioactivity. So this is a diagram, how the illustration diagram, how this that is a titanium fabrication using metal injection molding. Here you can see the titanium alloy and the binder is mixed. It is blended together. After that, using injection molding, the required shape is obtained. So after that, using debinding process or a sintering process. For an example, the debinding may takes place using either solvent debinding or it may can be made using thermal debinding. So this debinding will remove this how do you say that ceramic particles. So we will get the final raw materials. So here you can see, suppose we are mechanically blending titanium and HA powders, that is hydroxyapatite powders, and it is followed by pressing the powder in 6 megapascal and heating for 1000 degrees centigrade for 5 minutes. Their outcome will be released as the combination of titanium and hydroxyapatite materials, in which the inside porous this hydroxyapatite will be removed. However, the porous surface will be coated with this hydroxyapatite, which helps in improving the biological apatite inside inside this porous surface. The hydroxyapatite is present. It will create a better compatibility with the neighboring human tissue. Hence, they will improve the bonding of the materials. The next one is about titanium polymer composites. Here, so we all know the it faces a stiffness mismatch with the natural bone. So, in order this may lead stress, shielding, and potential complication. So, the polymers are added. So, these composites provide lightweight implants which may match the natural bone, which will reduce the stress shielding. So the polymers which they are using as also are polyethylene nylon, after that polyethylene terephthalate. So here you can see the diagram where the porous titanium structure and the titanium and the polymer composites, how they are made, how they align with each other. And another methods through which they can make the implants are using 3D printing. The final methods which using which they can make the materials are 3D printing. So in using 3D printing, either they will use direct metal laser sintering method, uh, or they will use selective laser melting, or they may use electron beam melting process. So in a direct metal lasering method, it is a popular additive manufacturing process where we can create a lightweight titanium for our optimized geometries. Here the laser power of 200 watt to 400 watt is used to create the 3D object. As the CAD file is according to the CAD file which was fed into the for the requirement. So here we can see. So the maximum density which is obtained is a 99%. So after that, this direct metal laser sintering requires post-processing processes to improve its further mechanical material properties. So this is a diagram. You can see the raw materials are fed, laser is fed. The next one is about a selective laser melting. The difference between this selective laser melting and direct metal laser sintering is uh, in a selective laser melting, the metal would, is completely melted when compared to the direct metal laser sintering. So that is the only difference. Here also they are using the laser for melting the process. The next one is about electron beam melting. This is also used to make the 3D model as per the requirements. Here we can see the electron beam. Here the raw material is fed. So using this, we can make the required 3D product. So these are the comparison between the various processes, that is direct metal laser sintering and selective laser melting and electron beam melting. So here you can see various operation principle, the various energy sources, what they are using, what are the environment they are using, material options, laser thickness, and surface finish, thermal stresses, and build rate. After that, the post processing is a comparison. The final one is about a titanium metal injection molding. This we have already seen in the metal matrix. It is a similar process. Here, the metal powder and binder is mixed and it is fed into the injection molding. After that, using deep binding, the binder is removed either using a thermal binding or a solvent binding. After that, we can acquire the final product. So this is a comparison between the additive laser manufacturing, that is 3D printing, and the titanium metal injection molding. So using these kind of processes, we can make the implant materials. So that is That's what I am trying to say. So the final conclusion is so titanium materials have is used in vast places in the human implants, and we have seen various types of titaniums, that is alpha, near alpha, alpha, beta, and beta alloys. With respect to the requirements, we can use the materials what we need, and with respect to the properties, strength, and resistance, we can use the what materials which we need, and we can also improve the biocompatibility, or we can improve the resistance. Uh, if you want to improve the corrosion, suppose it is kept on an area when there is more corrosion may take place, means we can improve the uh, the properties of the implant with respect to the area we are using, and we can incorporate the alloys with respect to that purpose. So this is the final conclusion, and we have seen the various uh, uh, process how we can make the implants. Um, that's all about my topic, and I thank you.
Thank you, Professor Ramkumar, for your deep and elaboration presentations about the titanium-based advancement of
Sir, can you hear me?
imaging
Sir?
devices. Yes, sir. Yes. Clearly, sir. From your presentations, we taken away from your various key points for improved biocompatibility, enhanced mechanical properties of titaniums, surface modifications, etc. Moreover, addressing the crucial requirement of present challenges and for future directions for its materials also we carried out, especially for wear and corrosion resistance, fatigue behavior through machine learning integrations, etc. The impact of implant and its personalized medicine revolutionized orthopedic implements materials also we can observe through your presentations. Thank you for your valuable presentations for this session. This is the forum to take the photo session. Dear participants, please switch on your camera mode for taking the photo session for this today's session. Thank you, participants. Questionnaire sessions. Resource person is here with us for your queries. If you have any queries, you can ask for put it in chat box. Professor, one question is here from Nilesh Rane. How to conduct validation for developed biomedical material? How to conduct validation for developed biomedical material?
Hello, sir. Can you hear me?
Yes, Professor. One.
So, as per the literature survey which I have seen, they are maximum they are getting the feedback from the patients only, sir. So they are conducting validation. Before that, they are having many survey methods. So after that, here they can validate only using the patient's feedback.
Thank you, Professor.
Thank you.
Nilesh sir, Kritik sir. Any other questions? For this today second session, feedback link is available in the chat box. Participants are requested to fill it. Uh, Thank you, Professor. I think no more questions available in chat box as soon as that.
Thank you, sir.
So, thanks for your presence. Spend with us your valuable time.
Thank you, sir. Thank you so much.
Thank you so much.
Shall I leave, sir?
Yes, sir. Thank you.